Then I hope you are all doing good. So in this video we will be going through histogram equalization. Now before even starting what is histogram, I will just again go through what is an image. So an image, as we know from our previous videos, is basically just a collection of numbers. Like it's a matrix and there are many numbers, some values here, and this is what an image all is. But how do we represent an image? Now obviously we cannot every time draw a matrix and say, okay, this is an image and these are the numbers. So instead we define an image using in a functional form, which is like this: f of x, y. So I can draw an image like this and say it has values 21, 10 and so on. But I can just write a function f of x, y, whereas when I give input as x and y, which are the rows and columns of this matrix, I get the value of its intensity. Now intensity can be RGB, or as of now we are only considering that it is a single number. So I mean, just giving an example, f of 0, 0 would be 21, and similarly f of 0, 1 will be 10, 0, 2 will be this value here. So this is how we represent any image. Alright. So now what is a histogram of an image? Now can you think of what would be a histogram of an image would be? Like how would it look like? So let's say, so there is another thing known as intensity level, which we must be aware of. So intensity level means, so it deals with how many different types of numbers can be there. And normally in images we have 256 as the intensity level, and this is usually represented by the letter capital L. Right, so by histogram and also given an image, we can calculate how many times does 0 occur, how many times does 1 occur in this image, and 2, and so on up to 255, because 256 is total, so the range is from 0 to 255. Now we can calculate this thing, right? We have an image, so we can calculate, okay, 0 has occurred 1020 times, 1 has occurred sometimes, and this. And similarly we can draw a histogram like this, so where this will be 0, 1, 2 up to so on and 255. And then we can plot this number. 0 is 1020, I mean, just drawing a row estimation, it may be here, then maybe this one, this, like this, and then when we join this, we get a histogram. Right, so from an image we can calculate the frequency of different pixels, and when we plot it, we get the histogram of an image. But now the question is, of what use is the histogram of an image? Why are we even interested in the histogram of a given image? Well, a histogram can basically tell us a lot about the image, a statistical point of view, which we cannot figure out straight away looking at the image. So in sometimes a histogram may be more intuitive to look at. Let's take some examples. So just look at this images here, right? This one. Now this is a histogram of an image, and all of these four are. But looking at the histograms, we can see that they are different in nature. So for example, this one, how can we figure out this histogram? What can we take out from this? Well, we can see that most of the pixels are located in this range, and this means in the lower range. So most of the pixels have low values, and what can we infer from it? We can infer that the image must be a very dark image, because it has really no light pixels. All of the pixels are dark. And again, if we see the image, I don't think I should hide it. So if we see the image, we can see it. All of the pixels are dark pixels, and so the image is a dark image. Similarly, let's take this one for example. So all of the pixels, or I should say most of the pixels or well, all of the pixels, yeah, all of the pixels are in the right hand side of the graph, all these bars. And what can we infer from it? We can infer that when we made this, so these pixels, the lower pixels, had all the values, and these pixels 0, 1, 2, they had nothing. So the overall image was light image. Similarly, this one, it has a very low contrast. We cannot differentiate between, there is no differentiation or no range of range of color, or because this is a grayscale image of light. So this is a low contrast image, and maybe like it may be tough to figure out a low contrast image and a dark image, but here we can see. Now if you look at the histogram in this one, it is spread out for over the all range, as compared to here where the range was very small portion of the total possible values that it can take. So this is a high contrast image. Just look at the histogram. I mean, we can just look at the histogram and see the difference. It has distribution of pixels over the entire range, and in this case it is just present in this given range. So I think this makes us clear on what we can do when we have histogram of an image, and why histogram is actually gives a lot of information about the image itself. I'm assuming that we have some information, we have some idea about what an image is and what its equivalent histogram is, right? So we know an image is, again, I will just draw the fancy matrix. So I will say this is my image, and then knowing this, I can draw the histogram, which may be something like this. And I know this is continuous. In our case it will not be continuous, basically it will be some bars, but this is actually easier to draw. This is continuous, but in our case it will be discrete, so it will have individual bars like this and not a straight and smooth graph. So I'm just drawing this because it is easier to do. Alright, so we have this image and we draw the histogram. Now my question is, let's say our given image is something like this, and we have image which is histogram is like this. Well, ideally this is preferred. I mean, this looks much better, right? So how can I convert a histogram, which is something a skewed histogram like this, and into something which is more constant throughout the domain or throughout the range of values? Can I do that? So what I'm saying is, I have this image and it has some histogram like this. Can I make some changes to this image so this is the changed image, right? I will again draw this fancy old matrix type thing. So I have this transformed image, and when I draw its histogram, well, it comes out to be constant. So what this means? This means that all of the pixel values are present. Theoretically, they are equal. Can I do that? Is it possible? I mean, yeah, it is possible, but can you think of any way that given an image, which has some histogram, I make some changes to the image, and now this image has histogram which is flat. And by flat histogram, I mean that all the values are present in equal component. So now let's see how we will approach it. Now first of all, the first thing is, what exactly do we mean when we say change an image or modify an image? Now I assume you know it already. This is the intensity transformation that we are talking about. So this is intensity transformation, and we had covered this earlier. Now what it means is that given the range, given some intensities in this image, which we'll call R, we can apply a function T of R, which will give us S, and this S basically represents pixels of this image. And interestingly, very interestingly, there is a TR, so S is equals to TR is equal to L minus 1 integration of 0, this should be integration of 0 to R P of R W P of R W dW. Alright, so this is some fancy looking equation. Now what is P of R here? So P of R is this distribution here. Now if we say that, I mean, let's say this is some random variable R, and this R is the random variable between all the pixel values that are present in the image, so from 0 to 255. Its distribution is P of R like this. And given this, and this is given because we can calculate this directly from the image, given this, we are calculating this S using this transformation function T of R, which is L minus 1 integration from 0 to R P of R W and dW, where W is just the used in integration, like the dummy variable. So interestingly, this fancy looking function, when we apply this transformation and we get a new image, this image will have a flat histogram. And isn't this amazing? So, and this also can be proved. So this can be proved using theoretically, and I will not go into that because it's given in the book. I mean, I don't want to go that deep, so we can refer to the book if you want. But the thing is that no matter what PR I choose or PR is available to us, this flat histogram would always be at L minus 1, 1 over L minus 1, where L is the intensity level in this case, which is 256. And well, this is the interesting thing I was talking about. So, I mean, just imagine any input distribution, any image we use, if we apply this transformation, we get a secondary image, and this image will have a flat histogram. Alright, so now this formula here, this is actually for a continuous variable. So in this case, this R is continuous, right? So it has a range of values and it can take any value in between. But in our case, R here basically represents some pixel values, and they can't be continuous, they are discrete. So pixel value can be 1, so starting from 0, 1, 2 and up to L minus 1. So like L is the discrete intensity levels that can be there, or L is the intensity levels. And since it is not continuous, so we cannot use this formula here, so we just need to do a little modification. So it will be S of k is equal to T of Rk, and this will be L minus 1, which is same as here, but now instead of this integration we will have a summation like this, which will go from J0 to summation J0 to K P of R of J, P of R of J. Now what do we mean by this? So let us go through an example and then we can know how to use this thing. So just as given in the book, let us take an image. So this image is 64 by 64. So there are 64 pixels here, 64 pixels here. So the total number of pixels will be 64 times 64, and this term comes out to be 4096. Okay, so this image is given, and we're now just taking like an example to see how this formula works. right? So this image is given. Now next thing is we do is we calculate how many pixels are of 0 are there. How many pixels are there whose intensity level is 0? By the way, this image is a 3-bit image. Now what do we mean by 3-bit images? That that any pixel can have 2 to the power 3 different values, which means 8. So any pixel can have value 1, 0, 1 up to 8, like this, up to 7 actually. It will be L minus 1. Yeah, 0 from, so any pixel here can take any value between 0 to 7. Now what we are doing here is we are just counting how many times has 0 occurred, how many times has 1 occurred, how many times has 2 occurred. So how do we calculate this? Well, just go through all the pixels and just check which value is 0, and then we have the count for that. So out of all the pixels, there are 790 pixels whose value was 0. There was 1023 pixels whose value was 1. There was 850 pixels whose value was 2, and similarly we do it for all the values from 0 to 7. Now the next thing is we calculate P of R, R of K, and this, what does this mean is what is the probability that a given pixel is 0, and how do we do that? Well, just 790 divided by total number of pixels, and total number of pixels is 4096 we have calculated here. So it will be just 790 divided by 4096, 1023 divided by 4096, which will give us the probability that any given pixel is 1. Or if we consider R as a random variable, it will give us what is the probability of R of 1, and like, which is what we have mentioned here. Now once we have this, so what we have now, like, what is the probability that R is 0, what is the probability that R is 1, and all the way to R of 7. Now once we have these values, we can actually have a very good plot of this. We can plot a histogram. So given in the book, this is how the histogram would look like. Again, it's no rocket science, like we just plot value of R of 0 here. R of 0 was 0.19, so we plot 0.19, then for R of 1 we plot 0.25, and similarly like this. So now comes this formula here. Now what is it representing? So this is intensity transformation function, and this will map the pixels of the image that we get after this transformation, which is S of k, to what we have currently, like R of k, and this is a map between both of them. So how do we go about it? So first of all, we will calculate like, let's say what is S of 0. Now what do we mean by S of 0? So S of 0 means whatever pixel here was 0. So in the original pixel, let's say this pixel is 0. In this transformed image, what would this pixel value have? Earlier it had 0, but now what it would have. So this is what we get by S of 0. And how do we calculate it? Well, just put k is equal to 0 in the formula. So we will have T of R of 0, and this will turn out to be as L minus 1. So what is L? L is 8 minus 1 times summation from 0 J0 to k, and k here is 0, from 0 to 0 P of R of 0. And what is P of R of 0? It is 0.19. So S of 0 will come out to be 8 minus 1, 7 times, so this is just one term here, and this is 0.19, and this comes out to be 1.33. Now what do we mean by 1.33? What does it mean that S of 0 is 1.33? Well, it means that every pixel that has 0 earlier will now be changed to 1.33. So this is what we are saying. Every pixel that has 0 earlier, so total 790 pixels, will now have the value of 1.33. And since the only values allowed are 0, 1 up to 7, so these are the discrete values which are allowed. So 1.33, we will round it off as 1. And similarly we can do it for s of 1. Now what would s of 1 mean? Well, all the pixels that had the value 1 earlier will now have the value s of 1. And how do we calculate it? That well, 7, l minus 1 will be the same, so l minus 1 will be same. Let me write it like this only. So 8 minus 1, which is l minus 1, summation j is 0 to 1, p of r of j. And now this summation term will have two terms, so it will be 7 times p of r of 0 plus p of r of 1, and this will then come out to be as 0.19, which is this value here, plus 0.25. And what would this be? 7 times 0.43, I guess. Yeah, 0.43, and 43 into 7, 21, 23. So this will be 3.01, right? Just let me confirm it. Actually this is 3.08. maybe I made some mistake here, so it is 3.08. yeah, like it's a bit difficult doing it live. So it is 3.08, and when we round it off it will be 3. So as of s of 0 was 1. Let me write it separately here, maybe using a different color. So s of 0, s of 1, similarly we'll find s of 2, s of 3, s of 4, s of 5, s of 6, and s of 7. So we just calculated s of 0 would turn out to be as 1. S of 1 would be like it was, I mean if we, yeah, it was 1.33, and we will round it off as 1. Similarly s of 1 was 3.08, and we will round it off as 3. S of 2, like if we calculate it similarly, s of 2 would be 4.55, and we will round it up to 5, yeah, because it's greater than 4.50. Then s of 3 is 5.67, we will round it off to 6. S of 4 is 6.23, we will again round it to 6. S of 5 is 6.65, and round it to 7. S of 6 is 6.86, again round it off to 7, and S of 7 is 7.00, again round it off to 7. And I think we can guess why this turns out to be 7, because, well, this would include l minus 1 and summation of all the probabilities, and summation of all the probabilities is actually 1, and l minus 1 is 7, 8 minus 1, 7. So once we get this mapping, so now we have this mapping, right? So 0 will map to 1, 1 will map to 3, 2 will map to 5. We can actually draw the relationship between S and R, right? So this is what is drawn here. So this is the transformation function, this is the input values, and this is what will be mapped to the output values, and this is not rounded off, so once we round off we will get much less steps. So yes, now we have the mapping. So now what we do, so now the next step is we calculate how many how many values of S will have 1. So now one thing that we can say is there is no 0, there is no 2, there is 3, there is no 4, there is 5, there is 6, and there is 7. There are some, so in the output image some values will not even occur, right? I mean, so what I'm trying to say is, like, if the input image, in the input image there is no value which maps to 2, there is no value which maps to 4, So the output values will also have no 2 and no 4, right? So now what we need to do is we need to create a similar map for these output image. So this, let's say this is a P of R. Let's use a different pen. Okay, we will clean this one also. I think we don't need this, so let's clean this up. And this, we got what we needed. So now let's see P of, let's actually use a different pen. Yeah, I think this is better. So now let's see P of S, R of K. How would this look like? So now there is no value which has 0. So N of K is so we will, okay, actually we will first need to calculate N of K. So this is 0. There is no value in S of 0 is equals to 0, it's 0. Similarly, S of 1 is equals to 1, S of 2 is equals to 2, S of 3 equal to 3, S of 4 equal to 4, S of 5 equal to 5, S of 6 equal to 6, S of 7 equal to 7. Now let's see N of K. So this is 0. Now how many S will have 1? And for this we will need to see where it's mapping. All the zeros now map to 1. So how many of them will have 1? Well, it will be the same as number of zeros, and this will be 790. Now how many will have 2? So there is no value which maps to 2, so it will be 0. Then how many will map to 3? Well, this will map to 3. So all the values which were earlier 1 will now map to 3. So this will be a 1, 0, 2, 3. Now how many 4 will be there? Well, again, no one. So no values actually map to 4. How many 5 will be there? Well, all the values which were earlier 2 will now be mapped as 5. And this will be 850. And then how many values will map to 6? Well, this will be earlier S of, all the values which were 3 and all the values which were 4. So it will be addition of these two terms here. And how many will that be? Well, just let me quickly add it. 656 plus 329. It will be 15. 5, 6, 7, 8 and 9, 985. And similarly, how many of the values will be 7? Well, all the values which were 5 earlier, 6 earlier, 7 earlier will map to 7. So this plus this plus this. Now let's see, 245 plus 122 and plus 81. So this will be 5, 6, 7, 8, 10, 14, 2, 3, 4, 4, 4, 8. And now similarly we can calculate P of S, R of K. And how do we calculate that? Well, it just is every number N of K divided by 4096, and I think this is doable. We can do that. And once we have these numbers, we can again draw a histogram, and this histogram will be the histogram of the final image that we get after applying the transformation. And what do we expect from this? Well, we expect that this histogram, which was earlier like this, should be a little more flat. Well, theoretically it should be completely flat at 1 over L minus 1. And what is 1 over L minus 1 here? So 1 over L minus 1 is 1 over 7, which is, well, I'm a little old school, which is 100 divided by 7, 7, 77, 84, 91. So on 13 it will be 91, and this will come out to be as 90. Oh, sorry, as 9. wait, I think I'm doing it wrong. So it will be something like my mind is just stopped working, so I will just take the help of Google. So it will be 100 divided by 7 is 14.28. So yeah, I mean, we expect this, that it should oh actually wait, 1 divided by 7, 1 divided by 7, 0.14, yeah, so it is 0.14. 0.14. So we expect that the histogram should be a flat line at 0.14. Now let's see whether this is true or not. Well, actually this is what we get. Now one thing to note here is that although the histogram is much more flatter than what it was earlier, but it is not true to the like original value, like the theoretical value that we would expect. Now we would expect that 0.14 may be something here, so it should be a straight line here, but well, it's not like that. But why? So one thing is for sure, that the histogram is more flat as compared to earlier, and also there is no 0 values, there are no 2 values, there are no 4 values, just as we find out here. There is 0, this is like 0, 0 and 0. But my question is, why is it not the theoretical value? Why is it not 1 over L minus 1? Shouldn't it be the theoretical value? Why is it not that? Well, I mean, according to me, see, we did some round off, right? So this was 5.67, we rounded off to 6, because well, in the output image we have this constraint that all the pixels will be like integers from 0 to 7, so we cannot have this as a pixel. So maybe it is this. So if we had much more values, like, I mean, as of now all the allowed pixel values were 0, 1, 2 up to 7. Maybe if we had, I don't think a real value is possible, but maybe if I had 0, 0.1, 0.2, all the possible values, maybe in that case the histogram would have been a much better, much more closer to the theoretical value, much more flatter. But I mean, this is not possible, so it is not equal to the theoretical value, it is not as expected. But still, I guess like it is much more flat. If you look at the curve, it is much more, if you look at the histogram, it is much more flatter than what it was before the transformation. So we can say that after applying this transformation, the histogram is actually much more flat. It is not completely flat as we expected from the theoretical values, but still it is like much flatter. Now let us see, we had seen an image earlier. So this image was this one, right? So we saw different images and we saw their histograms. Now the interesting thing is, how would the image be if we apply histogram equalization to this, histogram equalization to this, this and this? So what would the final image look like? And we can expect what the histogram would look like. They will appear to be more spread, and that like they will be like much more spread than this one. But how would it change the original image here? And how would all of these three, if you see, or all of the 4 images change if we apply histogram equalization? Now this will be interesting. Now let us see the output. So here we go, the dark image, right? So the dark image, if we apply the histogram equalization, comes to be something like this. And you can see now the histogram is spread out. It's not concentrated in this portion here like earlier. It is spread out. And also you can see, like, what is the difference between this and this? Here we have tall buildings. Let's use the word buildings. The tall buildings, but few in number. And here we have short buildings, but more frequent. So this is one like interesting observation that we can make. Now let us see this one. So originally the histogram was situated on the right hand side, But after applying histogram equalization, it is again spread out. All the histogram, all the intensity values are now spread out, and we can see that even if we start with a dark image, even we start with the light image, we get similar kind of images after applying histogram equalization. Now this was low contrast image and this was high contrast image. So in low contrast image, all of the pixels were situated in the middle portion. And after applying histogram equalization, well, it seems similar, isn't it? Similar to this image, similar to this image, similar to this image. So no matter where we start with, we kind of end up in the similar image, right? And same is this one. And if you remember, we had already proved this, that no matter what the initial distribution of pixels is, no matter what the initial distribution of pixel is, the output will be, theoretically it should be similar. Here it is not similar because, it's not exactly similar, but as we perceive it, we can see it's almost the same. Right, so this is like how we can connect the practical aspect of it with the theoretical aspect. Again, I say it's not exactly as it should be, but still it shows some properties that we can find out. So yeah, I guess this was it. Now I will also mention in description a video in which I try to implement histogram equalization from scratch. So hope you enjoyed this video. This was just a natural I don't script it, it's just a natural me speaking. So hope you enjoyed it. Thanks, bye, namaste.